All right, here we are for another lab. This is the last lab of the GChem 2 lab series, and it has to do with electrochemistry just like the last one did. Whereas the last one dealt with Nernst equation, and the Nernst equation tells you the potential based on a non-standard state condition. Of course, you do the standard state condition from the standard state reduction potential tables. So for this one, we're going to deal with non-galvanic cells. Nernst equation basically was dealing with galvanic cells. Galvanic means that the cell will run spontaneously in the direction as it's written. That means that if we hooked it up, whatever it was, zinc and copper, it would run such that the zinc, which is zinc undergoes oxidation much easier than reduction. Therefore, zinc would be the anode, copper would be the cathode. Because remember, the site of reduction is cathode, the site of oxidation is anode. So zinc undergoes anode very easily, so it would be, it undergoes oxidation very easily, therefore it would be the anode in a galvanic cell. The other kind of cell is an electrolytic cell. Now, when you get up in the morning, you got to go to work or maybe you got to go to class, you get in your car, you turn the key, your battery in your car is a lead sulfate combination battery. When you turn the key, the battery is acting as a galvanic cell. It is supplying power to turn your starter motor. Once your engine starts, the generator begins to put energy back into the battery to recharge it. While it's being recharged, that means it's an electrolytic cell. It is being charged up. It is running in the opposite direction that it would normally run spontaneously. Therefore, you're putting energy into it and charging it back up. And that's the difference between electrolytic cells and galvanic cells. Electrolytic cells run opposite to the spontaneous direction, which means you must apply a potential in the opposite direction greater than the spontaneous potential that those cells would develop. All right, we're going to use this to find out, to do a determination of Avogadro's number. And of course, you know Avogadro's number is what? Well, you probably know the value, 6.022 times 10 to the 23, which is a tremendous, huge number of things. I think I did the calculations many years ago that if I gave you an Avogadro's number of dollar bills, you could spend $1 billion a second, every second, and the sun would burn out before you could spend all that money. That's how big an Avogadro number of things are. Now, Avogadro's things we always apply to a mole, and we always apply it to atoms or molecules. But Avogadro's number simply is the number of things in a mole. It's like 144 things are in a gross, 12 things in a dozen, 13 in a baker's dozen, whatever. It's just the number of things in a mole. And of course, Avogadro created this number for this reason, right? No, Avogadro didn't know anything about Avogadro's number. Avogadro was dead for years and years before Avogadro's number was even calculated the first time by a fellow named Loschmidt. Avogadro knew nothing about Avogadro's number. So why is it called Avogadro's number? Well, it's called Avogadro's number because there was an Italian scientist that was a big fan of Avogadro. And so when this number came up, this fundamental number came up, he petitioned to have it called Avogadro's number. Why? Well, there is a basis for it. Avogadro had a gas theory, and hopefully you learned about that this term, that there was, or last term in GChem 1, right? There's Boyle's, there's Charles' theory. Avogadro's theory was one of those gas theories that led to the ideal gas law. And Avogadro's theory was that the number of things at the same pressure and temperature in the same volume is the same number of things. Didn't say what those things are, and that's pretty much true for ideal gases, and most all gases behave ideally at high temperature and low pressure. So that was sort of the basis for determining Avogadro's number initially. Because of that, he petitioned to have it called Avogadro's number, and it was. We're going to calculate Avogadro's number kind of a different way. We're going to do that with electrochemical principles and basically electrolysis, and that is the application of running a cell in the opposite direction than it is. All right, so how do we go about doing that? Well, we need to know some of the fundamental principles of electrochemistry that was developed by Faraday and a few others a long time ago. So what are those things? Well, let's say that we run a potential to we have two different cells. We have a cell over here that has, say, zinc sulfate in it. right? And we have a cell over here, and this has zinc sulfate in it. So we've got these two cells, and they've got a solution in it, and the solution is at a certain concentration of zinc sulfate. Now, we know zinc sulfate is an ionic compound. Ionic compound in aqueous solutions go into the solution as their ions. Therefore, there is no zinc sulfate in this solution. There is zinc 2+ ions and sulfate 2- ions. Okay, so then we're going to connect these with a salt bridge, and we have to connect everything with a salt bridge because we can't have a charge develop. If I was running something to where I was reducing the zinc 2+ ions in solution and plating them onto a zinc electrode, say this is pure zinc electrode, right? Zinc, no 2+, no solid. It's a solid, not an ion. If I was plating them onto there, I'd be removing 2+ ions from solution and not 2- ions, because what's plating on here is zinc solid, not zinc ions, zinc solid, and I'd be removing zinc ions. So therefore, this would start to develop a negative charge. Well, the negative charge would get great enough that I couldn't get the positive ions to move away from the negative solution to get onto the surface of the electrode because they'd be too strongly attached to that solution. So I put in a salt bridge so that these counter ions can run, and typically use KCl, and the reason for that is that the potassium ion and the chlorine ion are both about the same size, and therefore their mobility is about the same. So that as I was removing 2+ from this, there would be potassium K+ ions would move into the solution. As I was removing, as I was adding more zinc 2+ ions by dissolving this electrode, that again was made of a zinc metal, as I was dissolving it and getting more chlorine ions would move in there to offset the charge, so that the electrons could flow. Okay, so let's say I do that, and I find that there is a change in the mass of the electrodes. Why? Because zinc 2+ in solution is being plated onto this zinc metal. Zinc metal in this solution is being removed and increasing the number of zinc 2+ ions in solution. I'm dissolving this electrode. I'm plating this electrode. And of course, they have to be attached so that voltage is applied to make that run in whatever direction I want it to run in. Okay, for what we're doing, it would be the opposite, spontaneous, but regardless, we're doing the same ions here, so it doesn't make that much of a difference. So I'm going to remove ions, I'm going to plate ions over there. Well, I can mass them out, and of course I know the change in mass is going to be final minus initial, so it's going to be the electrode mass, if I can write it, electrode mass final minus electrode mass and that's going to tell me what mass has changed. It doesn't tell me the number of atoms that's changed. But of course, using the molar mass of zinc, I could figure out how many moles of zinc was plated to this one and was removed from this one, right? From that mass, I could figure out the number of moles. So if I want to calculate Avogadro's number, then I'm going to need number of things over top of moles, right? Because that's what Avogadro's number is. It's the number of things in a mole. So if I know the number of things, I know the number of moles, that should give me Avogadro's number. So to get the number of moles, I simply take the mass divided by the molar mass, right? Because if I have mass of zinc divided by, and the molar mass is what? Molar mass is grams per mole. So that's mass of zinc per mole of zinc. So if I take mass of zinc divided by mass of zinc over mole of zinc, masses cancel out and I get the number of moles of zinc. So, zinc. So if I ran this experiment for a period of time, and then I shut it off, rinsed off the electrodes, dried them, and I remassed them, by the change in mass, I could determine the change in the moles on the surface. Now, for one of these, it would lose mass. The other one would gain mass. And theoretically, it would be exactly the same because the number of moles removed from one would be the number of moles plated to the other one. Okay, fair enough. Which one's going to get plated? Well, remember, Anode is always a site of oxidation. Cathode is always a site of reduction. And you know that because anode and oxidation are both vowels. Cathode and reduction are both consonants, so you can figure that out. All right, so what are we going to do? So let's say this one is the anode, just so we have something to say, and this one is the cathode. Cathode is always a site of reduction. If it's a site of reduction, what would be the reduction? The reduction would be the zinc 2+ ions in solution being reduced down to metallic zinc. Therefore, this would be the one that's being plated. Therefore, this is the one that would increase in mass. Anode, the site of oxidation. Well, what's oxidation? Oxidation would be the zinc metal, zinc solid, going to zinc 2+ in solution. Therefore, this electrode would be dissolving. So the anode gets dissolved. Anode gets dissolved, cathode gets plated. Okay, fair enough. So I figure out the mass. I run this for a period of time, whatever the time is. I run it for a period of time. That's T for time. And then I dry off the electrodes and I mass them out and I figure out what mass changes there are. Based on the molar mass of zinc, I can figure out how many moles were transferred over there. I don't have the molar mass of zinc off the top of my head, and I'm not going to stop the video to look it up because we're doing the theoretical part here. We'll do an example in a second. Okay, so I've got, what do I want? I want Avogadro's number, and that's going to be equal to number of things, this is the way we have to think about it, over number of moles. Okay, so I've got my number of moles, right? Because I can take the molar mass of zinc that changed, I can take the mass of zinc that changed divided by the molar mass of zinc, and that gives me the number of moles of zinc. Okay, so I've got half of my value. I've got that value. I need the number of things. How do I get the number of things? Well, this is where the electrolysis comes in. So there's a couple of things I need to know. I need to know some definitions. In electricity, in electrochemistry or whatever, the current that flows is equal to the charges that move over unit time, over some time period. So if I'm going to say what the current is, and current is given in amps, if I'm going to say what the current is, I have to figure out how many charges flow past a point over a given amount of time. Okay, so if I look at the definition of an amp, and A, capital A is given as amp, an amp is equal to the number of coulombs that flow past a point per second, every second. So this is amp. Amp is A. That's current. That's a measure of current, and that measure of current is defined as coulombs per second. Charges per unit time, coulombs per second. So if I rearrange this, I can see that a coulomb is equal to an amp second. That's amps times second. So if I know how many amps and I know how many seconds, I can figure out how many coulombs must have flowed past that point. Okay? So the average number of amperes over the given time in seconds is going to give me the coulombs that flowed past that point during the experiment. So why is that important? Well, then we look at something else and we find out that an electron has a charge on it of 1.602 17733 times 10 to the negative 19 coulombs. Would you be expected to know that number? No, I had to look it up when I'm writing it down right now. I just don't use it that much. Avogadro's number, 6.022 times 10 to the 23, that you should know. But this number, the number of coulombs in an electron, that's E minus for electrons. Wouldn't expect you to know that. Okay, so if I can figure out the number of coulombs, I can take the number of coulombs and I can figure out the number of electrons, right? Because the number of electrons this is how many coulombs there are in an electron. So if I take the coulombs divided by let's make sure we work it out. If I know the number of coulombs, I have X number of coulombs. Let's say I have 3 coulombs, and I know that each electron is 10 times 1.6022 times 10 to the minus 19 coulombs. That means that if I take it times an electron, and remember, this is the way you always want to set things up. I just look at my definitions. I'm not going to leave myself enough room there. And I can figure out how to calculate it out. If I take this, that tells me that 1 Another definition of 1 is an electron over 1.602177733 times 10 to the minus 19 coulombs, right? That's another definition of 1. Why is that a definition of 1? Well, each electron has that many coulombs of charge in it. Therefore, if I divide it through, I get 1 equals, these things are equal. So 1 electron is the equivalent of 1.60. That's my unit that I use to change values with. Let's make a little room here. So I don't have to memorize anything. If there's 3 coulombs that flowed, then that times E equals 1.602177733 times 10 to the minus 19 coulombs. Coulombs cancel out, and I get the number of electrons that flowed. Okay? So I don't like having to memorize things and saying, oh, when I'm given this, I do that. Just look at the definitions and work it out. And that way I don't have to memorize anything, and I can still do the math correctly all the time. So this would give me the number of electrons. Okay, fair enough. But what good does that do me? Well, I know, and especially after doing the zinc stuff, I know that if I have a zinc, right, and it's going to go to give me zinc 2 plus, it's going to go to give me zinc 2 plus 2 electrons, right? And I know it's zinc 2 plus. Why? Well, because all the transition metals, you have to indicate what the oxidation state was, except for 3. And what were those 3? They were 3, right? It's silver, cadmium, and zinc. And you don't have to do it for silver, cadmium, and zinc because silver is always +1, cadmium and zinc is always +2. So I know it's going to be +2. There's going to be 2 electrons. Therefore, for every 2 electrons transferred, 1 zinc atom was either oxidized or reduced, right? It could either go in that direction and it gains 2 electrons to go to here, and it loses 2 electrons to go to there. This direction would be oxidation. The number increased from 0 to 2, oxidized up. Reduction would be in this direction because it went from 2 plus to 0. That's a reduction in the number. And therefore, this way is reduction, that way is oxidation. And how many were transferred? Well, I take my number of electrons. Let's say I have x.xx electrons, and I know that for every zinc atom, and I can use atoms or ions interchangeably here because the addition or subtraction of 2 electrons is trivial, divided by 2 electrons, because again, this tells me that that's the same thing, right? If I look at this, I turn this into a ability to change my dimensional analysis. I can see that if I divide this side by this, it would say that 1 equals zinc over top of Zn2 plus 2e minus. And therefore I can say zinc plus 2e's is the same thing as zinc 1. So I have that, and this would be the zinc atoms would cancel out, the electrons would cancel out. That would tell me how many zinc atoms transferred. Does that make sense? I know I'm going through it pretty quick, but we've done this like a bazillion times, so hopefully you can follow it pretty quickly with what I'm saying. Again, I don't like memorizing anything. I just know, if I know, well, I do. I memorize the definitions. If I know what the definition is, I know what that equation is, I know what that balanced chemical equation for zinc is, I can figure out what the factor is I use to change the values of something. Same thing with knowing, these I wouldn't expect you to memorize, but, if you're given the definition, you should be able to work that out and then figure out what it is from that. All right, let's do an example. That's a lot of me rambling on stuff hopefully you already understand. I'm just going through it again. It's kind of a review. So let's do an example. So this is in the handout. Let's do a sample calculation for a zinc electrode and zinc sulfate, just like we did. And the reaction ran for time equals 25.00 minutes. And the amperage was 0.65 amps. And we found that one of the electrodes' initial mass was 9.361 grams, and the final mass was 9.0442 grams. So did this gain mass or lose mass? It lost mass. If it lost mass, which one was it? Was it the anode or the cathode? It was the anode, right? Because the anode is the site of oxidation. And oxidation in this case would be the zinc going from zinc metal to zinc 2+. The oxidation number increased. It didn't reduce, it increased. Therefore, that's the site of oxidation. And therefore, that's the electrode that would lose mass. All right. Good enough. Now let's go through and see what we can do. We should be able to figure out the mass change and the number of moles from this, but let's go ahead and see how many atoms were transferred first. So we know that 1 amp second equals a coulomb. So we have 0.65 amps, and we take that times 25 minutes. But we got a problem. This says it's amps per second, not amps per minute, so we have to also put in our factor here, which tells us there are 60 seconds in 1 minute. Now notice this is a definition. The significant digits don't change. There is exactly 60.000 infinitely in 1.00 infinitely minutes because it's a definition, okay? So that's not going to change my units. And that means I'm going to have what? 9.75 times 10 to the 2 coulombs. Of course, do that in your calculator. Make sure I'm calculating it out correctly because I could mess things up. All right, so that's how many coulombs. All right, we got a number of coulombs. From coulombs are the number of charges that flow past a point. We want to know the number of electrons. And each electron has a certain charge on it. Therefore, let's figure out how many electrons there were based on how much charge there was. So we have 9.75 times 10 to the 2 coulombs. And we know that 1 electron has 1.6021773 times 10 to the negative 19 coulombs on it. Now notice I use so many numbers here, that way I know it doesn't change the whatever number of sig figs I have here. It doesn't change the number of sig figs here. So that's why I use this huge number. You don't have to. I mean, if you went to 3 decimal places or 4 decimal places, that would be fine. But I got it, so I might as well use it. And that tells me there were 6.09 times 10 to the 21 electrons must have flowed past there to give that number of coulombs. Now notice I'm still using 3 sig figs, carrying a guard digit, so I don't do a rounding up bias or anything like that. So now I got the number of electrons transferred. Okay, great. I'm halfway there, right? Because all I need to know is the relationship between the number of electrons which flowed and the number of atoms which were transferred during that flow of electrons. Well, that's pretty simple because if I look at my equation, I know that zinc solid is going to go to give me zinc 2 plus 2 electrons. Beautiful. Therefore, my 6.09 times 10 to the 21 electrons, and that is 21 electrons. Let me correct that, make sure that it's clear. It's 21. 21 electrons. I'm going to take that times what? Well, for each zinc solid, there was 2 electrons. You could do zinc 2 plus up top here if you want to. Like I said, the difference in the ions and the atoms is sort of irrelevant. So that tells me that there must have been 3.0, and if I'm going to take half of 9, that's going to end up giving me 4.5 down here, times 10 to the 21 zinc atoms. Okay, I now have my Avogadro's number is number of things over number of moles. I've got my number of things. That's going to be 3.045 times 10 to the 21. I always want to put a negative in there. 21 zinc atoms. I need to get the number of moles. How do I do that? Well, I know that my change in mass, and I want the change in mass, and that's going to be to my electrode final, which I said was 9.0442 grams, minus the initial, which was 9.361 grams. Remember, it's always final minus initial. And that tells me that there was a change. Now, I don't care whether it's negative or solid, negative or positive. Solid. Where the heck did that come from? So we can say that we're going to use the absolute value of this change, because we want the change of mass, not whether it was lost or whether it was gained. It doesn't make any difference. We're going to use that mass to determine the number of moles of zinc atoms that were transferred. Whether it was lost or gained, irrelevant. So we're going to use absolute value of it. So the absolute value of that is going to be 0.3229 grams of zinc, and therefore 0.3229 grams of zinc times 1 mole of zinc is 65.409 grams of zinc. And therefore my grams of zinc cancel out, my moles of zinc comes through, and that means that would have represented 4.9366 times 10 to the negative 3. That's where the 3 was coming from. Moles of zinc. Now I've got my number of my moles, so my Avogadro's number must be 3.045 times 10 to the 21 atoms, which I keep putting an extra letter in there, and I don't know why. 4.9366, except it's getting near the end of the term, and I don't know about you, but it gets a little, you're about ready for the term to be over. It's been a lot of fun. I've enjoyed having you guys, but still. So now I've got moles per atoms, and gives me Avogadro's number of 6.1 times 10 to the 23. That's not bad. 6.1 times 10 to the 23 compared to 6.022. You can figure out the percent error. It gives you the formula for doing that in the lab. And usually we're pretty close. This lab usually works pretty good. When we do it in the laboratory, you're going to be doing it with a simulation. It should work even better because that's more or less theoretical. When we do it in the lab, we actually do this, only we do it with copper. And we apply potential, and we do the copper in one direction, and we go and do the copper the other direction. And we usually get an Avogadro's number that's, about 5% or less error in it, which is pretty darn good. Okay? So this lab is pretty easy. Shouldn't take you very long. Get it done. You need to turn it in the Monday of Thanksgiving week. Now, of course, you can turn it in before that. I'll open it up extra early. That's because that way you'll have Thanksgiving week off. You'll have the week after to just study for your finals and everything else, because this lab will be done. We will be done with this lab. Okay? Again, I hope you guys learned a lot this term. That's the big thing. I know that it is, GChem 2 comes at you fast and furious, and there's a whole lot of concepts and a whole lot of stuff, and it's all being slung at you really quick. Everyone did very well this term. I don't even know if there's going to be any B's. There should be some, almost all A's. If you need any help for preparing for your finals in this class, the lecture or whatever, shoot me an email. Let me know. If enough people want to do it, we can make up a big Zoom session and get together and work out problems and go through some stuff. If not, then have fun, and maybe I'll see you in another class, maybe quant over the summer. Hopefully by then we won't be doing the remote instruction anymore, but I don't know. Otherwise, I enjoyed it. I hope you learned a lot. Have fun. Stay safe.